So for this example, we have a set H where we have a variable s, a variable t, and then 0 at the end. So what we need to do is we need to show that H is a subspace of R3. In order for H to be a subspace of R3, we need these three things to hold true. The 0 vector of V is in H is closed under vector addition, and H is closed under multiplication by scalars. So for the first part A that is, we will have a vector which consists of S being equal to 0, T being equal to 0, and the last part is always 0. Now notice that we can actually do this because 0 is a real number and S and T are both real numbers. So all of these three are 0, therefore the 0 vector of V is in H. Now for part B, we will have two vectors, U and V, which are both part of H. If we add these two together, we're trying to prove that it's closed under vector addition because we're adding two vectors of the space H together. Now notice we'll have U1 plus V1, which is the first part of U and the first part of V added together, U2 plus V2, and then 0 plus 0. So because U and V are part of H, and U1 for U is actually just S, and S is a real number, same with V1, a real number, same with U2, that's corresponding to T, and V2 corresponds to T as well, and that's also real. If we add two real numbers together, we will get another real number, which we can just consider to be S and T. So in the end, we'll have S, T, and 0, which is within the subset H. So for C, very similar to B, except we're just multiplying. So we multiply U1 by V1, U2 by V2, and then since we're multiplying a real number by a real number, we get another real number. So S, T, and 0 proves that H is closed under multiplication by scalars. So since these three examples hold, and we have proven all three, then we've shown that H is a subspace of R3. For this example, we're going to show that the set H of all points in R2 of the form 3S and 2 plus 5S is not a vector space. We're going to do this by showing that it's not closed under scalar multiplication. So first what we're going to do is we're going to write out the vector in vector form. 2 plus 5S, so we can see it more clearly. And then what we're going to do is we're going to find some S and some C, such that this is not a true statement. So to make things easy, we'll just pick S equals 1. So that is going to be equal to 3 times 1, which is 3, and then 2 plus 5 times 1, which is 7. So this is the resultant vector if S equals 1. And then we're going to choose some scalar, which we're going to say is 3, or any number. So now, now that 3 is a scalar that we're using, we're going to say 3 times the vector 3, 7. That's going to be equal to 9 and 21. So since we have this vector, 9, 21, which is resulting from our S equaling 1 and C equaling 3, then that must mean that 3S and 2 plus 5S holds true for this same vector. So let's try to verify that. So on the first row, we have 3S equals 9. And some simple division will show us that S will equal 3. And so we're going to have S equals 3. And then so in the second row, in the first row, we'll have 9 if S equals 3, and if this holds true. And then the second row, we're going to have 2 plus 5 times s, which is 3 in this situation, and that's going to be equal to 17. So we're going to have 9 and 17 as our vector if this was true, and we used these combinations of numbers. So we see that 9 is not equivalent to, 9, 17, this vector right here, is not equivalent to 9, 21, which means that this vector, this set is not closed under scalar multiplication. So therefore, it is not a vector space. So for this example, we have vector A, vector U, and vector V. Firstly, we're trying to determine if U is in the null space of A. So in order for U to be in the null space of A, we need A multiplied by U to be 0. And if we look at the product of this matrix multiplication, then we'll find that we get a vector with 0, -3, and 3, which is not a 0 vector. Therefore, since AU is not a 0 vector, U is not in the null space of A. Second, we're going to determine if U can be in the column space of A. And in order for U to be in the column space of A, it must be a linear combination of the columns of A. So if we look here, we'll see that the number of components in each column of A is equal to 3. Notice how each column of A has 3 different components. And the number of components in U is 4. So it's impossible to set this into a system of equations to determine. So therefore, U is not in the column space of A. Now we want to determine if V is in the column space of A. So in order to determine if V is in the column space of A, we actually need to set this into the form of AX equals B. So what we need to do is we need to make one single matrix, which is A and U concatenated. So once we reduce that into reduced row echelon form, we find that our system is consistent and it has one free variable at x3. Therefore, V is in column space of A. Lastly, we want to determine if V could be in the null space of A. In order to do this, we need to check if A multiplied by V is 0. Now, first off, we need to make sure that it's possible to do matrix multiplication. So we need to make sure that the number of columns in A is equivalent to the number of rows in V. And as we look, we'll see that the number of columns in A is 4, and the number of rows in V is 3. So this is impossible to do any matrix multiplication. Therefore, V cannot be in the null space of A.